Assalamu alaikum. Today I will presenting rectangular waveguide. My name is Muhammad Emon, ID 200021332. So let's start. Today for the rectangular waveguide we will topic these topics. So at first I will give a short introduction to waveguide. Then I will go directly into the rectangular waveguide and the structure, modes of rectangular waveguide, cutoff frequency and wavelength of cutoff wavelength of rectangular waveguide, intrinsic wave impedance of rectangular waveguide, group velocity, guided wavelength, and also at last we will see why transverse electromagnetic wave cannot propagate through the rectangular waveguide. Moving on. So waveguide, what is a waveguide? A waveguide is a physical structure that directs electromagnetic waves from one point to other, usually with minimal loss. It works by confining the wave within its walls and guiding its propagation, typically used at the microwave and optical frequencies. There were different types of waveguides, such as parallel plate waveguide, in then rectangular waveguide, circular waveguide, slab waveguide, optical fiber. Um, Such as in parallel waveguide, waves are propagated through two conducting plates, usually metal, separated by a dielectric. In the rectangular waveguide, which we will study in detail today, it is a hollow metallic rectangular tube that confines and guides electromagnetic waves. Okay. Um, at first, let us know the applications of rectangular waveguide. Um, in radar systems, satellite communications, microwave ovens, antenna feeds, and in various test equipments, the rectangular waveguides are used. Moving on. So here is the structure of the rectangular waveguide. It is a rectangular conducting tube of width A and height B, filled with dielectric epsilon r and relative permittivity mu r. In this structure, fields are entirely contained, and this waveguide is commonly empty, so it passes the loss of dielectric and also offers high single mode bandwidth. However, it is not efficient. Now, we also now need to know about two notations. One is this n and sorry, pardon me. So one is this n and another one is this m. So why these are used? Here m represents the number of half-wave variations along the width A, and the n represents the number of half-wave variations along the width B. So these m and n notations are used to define modes of operations such as TE10, TE11, TM23, and so on. So there are different modes in rectangular waveguide. One is the TM mode and then it's the TE mode. However, TEM mode does not exist in the rectangular waveguide. The detailed proof why it doesn't exist we'll see in the later part of the video. Okay, so at first the transverse electric modes are in rectangular waveguide. So here we can see 4 pictures, all are the rectangular waveguides. First let me tell about what is this view. This is you can say the front view of a rectangular cube. So this is the x axis, this is the y axis, and through the page it is the z axis. So when in the first picture, in the first rectangular waveguide, we can see there is just one variation of transverse electric modes and just one variation along the transverse electric mode. So this m will be 1 and this n will be 1, so this is called the TE11 rectangular wave. Another one we can see here we can see along the n axis there is 2 variations. So along the m axis there is 2 variations, so m equal 2, and along the n axis there is along a there is 1 variation, so n equals 1. So this one will be 3e to 1 mode. Here we can see along the x-axis there are three variations, so n equal 1, and along the y-axis there is no variation, so uh, t so m equals 0. Similarly here, along the y-axis there are three variations, but along the m-axis there is 0. So that is why it is 3 TE30 rectangular waveguide. Moving on to the TM modes. So moving on to the TM modes. First, we can see here, um, for TM mode, here we can see that the rectangular waveguide is having one line trace out with respect to A, and one line trace out with respect to B, so it is a TM11 mode. Similarly, we can see that uh, the rectangular waveguide is having 3 trace out with respect to B and 2 trace out with respect to A, so that is why it is a TM23 mode. For also, it is to note that for TM modes we cannot have the TM10 and or the TM01 mode, since it is not possible, which we can see from the picture. This mode is called the event scan mode. Moving on, there is also degenerate mode. It happens when A is equal to B, so if A is equal to B, then TE43 and TE34 becomes 1, and they also contain the same cutoff frequency, and this scenario is called the degenerate mode. Also, there is dominant mode. I have mistakenly written here TM modes. This is both for TE and TE, so this will be for the TE mode. So TE10 mode is the dominant mode, since it has the least cutoff frequency. Okay, moving on, about cutoff frequency and cutoff wavelength. So the condition for wave propagation is that the operating wavelength must be greater than the cutoff wavelength, and vice versa, the cutoff frequency must be less than the operating frequency. What are the formula of this? The cutoff wavelength formula is here, 2ab by root over m square b square plus n square plus a square, and the cutoff frequency is here. So the m is, we all know that we have studied earlier, the the half wave variations along with A, and n is the half wave variations along with B. So for like from here we can find those cutoff frequencies and wavelengths. Intrinsic wave impedance, this is the formula for the intrinsic wave impedance for the TE and TM modes. So eta TE equal 120 pi divided by root over 1 minus FC by f squared. We can also write that as 120 pi by cos theta, and similarly eta TM. However, TM intrinsic wave impedance doesn't exist, as we have said earlier. Moving on to the rectangular waveguide's group velocity. So how does the rectangular waveguide propagate? So basically we have a wave, so that is like this sine wave. Let me see if I can manage. Yeah. So it is propagating like this. So it is propagating along the z-axis. This is the y-axis, and it is being reflected, since it is a hollow tube, conducting tube. It reflects, so it reflects along the x axis. So it goes like this, and this. So it can be shown here. Okay, moving on. Sorry, let me erase this. Okay, so moving on. So how it is calculated? It is calculated like this. The wave propagates like this. So this is it. This to this goes in the speed of time, in the speed of light. Sorry. So from A to B, we can see here C equal dAb by t. However, group velocity is defined as defined the velocity from A to C. So we can write it like this: the DAC, the distance between A to C, divided by the time taken from going to A to C. Moving on, here is the detailed formula for the group velocity as well as the phase velocity. So for the group velocity, we can see Vg equals c times root over 1 minus fc by f squared, and phase velocity is c divided by root over 1 minus fc by f squared, and the multiplication of the phase velocity and the group velocity is c squared. It is to mention that the phase velocity is always greater than c and the group velocity is always less than c. Okay, now let us move to the last section of our video. Okay, now we'll see why transverse electromagnetic waves cannot propagate through the rectangular waveguide. Um, First of all, what is the transverse electromagnetic wave? It contains both the electrical and magnetic field, and the components along the Ez and Hz is 0. However, the component along the x and y axis electrical field and the magnetic field is not 0. So if it fulfills, then it can propagate. However, it cannot propagate. So we know the equation for the transverse electric wave. It is del squared Az equal negative omega squared nu epsilon Hz, and for the transverse magnetic wave, it's del squared Ez negative omega squared epsilon nu Ez. So we'll define it as equation 1 and equation 2. Moving on, from equation 1 was the del square Az equal minus omega squared nu epsilon Hz. So we will now deconstruct this del squared and then multiply. So we can after doing that, we can see this comes and notate del squared del z square equal gamma squared. So doing this, and we at last get this equation: del squared Az by del x squared del y squared Az and plus h squared Az. H squared is defined as like this. Okay, moving on. This was for the transverse electric wave. For the TM wave, we can similarly find this equation as well. Moving on. This is the Maxwell's equation. So del time cross H equal j omega epsilon E. So deconstructing it, we get this. Moving on, we get so after doing this, we just take the components of I, J and K and match it with this one. So doing this, we get these three equations, this one, and this one. So we'll notate this as C, D and E. Again, for another Maxwell equations is this one: del cross E equal negative j omega nu H. So taking the I, J and K components, we get these three equations. So after solving these all A, B, C, D, E, F, G, H, G and H, we get these equations Ex, Ey, Hx and Hy. Now as per TEM waves, we know the Ez and Hz is 0. So putting those in these equations, we get basically Ex, Ey, Hx and equals 0. So which means there are no components along the along any axis of the rectangular waveguide. So that is why you can tell that the TEM cannot propagate in the rectangular waveguide. So this is all from me. Thank you for your time. Assalamu alaikum bhai.